Okay. So, as promised in the last lectures, our aim will be to prove the Radon-Nikodym theorem. However, we need some elementary results about the space L2 of mu. So, recall that we defined LP of mu, where mu is a positive measure, and we proved that it is a complete metric space with respect to the metric given by the norm LP norm, right. So, among LP, L2 has a slightly better structure, in the sense that there is an inner product there, which makes certain things very easy. So, we will discuss those results first. These are, consider these as auxiliary results, and you will see much more general results when you do functional analysis later. However, what we need about L2 is a fact about continuous linear functionals. So, this is more like a Riesz representation theorem, if you like. We will use that in the proof of Radon-Nikodym theorem. Okay, so let us start with the space L2 of mu. So, recall. Okay, so well, let's give this title some results on L2 of mu. Okay. So, we have x f mu. So, we are not assuming, so mu is a positive measure. We do not need to assume that it is sigma finite now. We define the space L2 of mu, right, LP of mu, in fact, p equal to 2. So, this has, so what is this? This is the collection of measurable functions on x, such that the integral of mod f square d mu is finite, and we define the L2 norm of f to be the mod f square d mu, and then take the square root. So, if it was LP norm, we will be raising the power to p and then taking a pth root, right. So, this is the L2 norm. So, recall that we made L2 mu into a space of equivalence classes, so that this is actually a genuine norm. Okay. Now, with L2, the advantage is it has an inner product. So, L2 mu has an inner product, okay, which gives, so let us write this as Fg inner product. This is equal to integral over x f g bar d mu. Okay. So, the right hand side is a complex number, and it is finite due to Cauchy-Schwarz inequality. So, let us recall the Holder's inequality for p equal to q equal to 2. So, that gives me L2 norm of f, L2 norm of g, right. So, this is the Holder's inequality which we proved, Holder's inequality for p equal to 2, okay, which is the Cauchy-Schwarz inequality. So, this is also called the Cauchy-Schwarz inequality. So, our aim in this session and the next session would be to study L2 mu a little bit more carefully. So, consider, so let us fix a g in L2 of mu, and consider the map f going to inner product of f with g. Okay. Let us call this map T. So, what do I mean? T of f equal to integral over x f g bar d mu, right. That is the inner product, right, f g. Okay. So, where is the map going from? Is defined on, it is defined on L2 of mu, and it takes values in the complex plane. Okay. Well, this map has certain properties. So, let's try to understand that. The map T from L2 of mu to the complex plane is linear. It is a complex linear map. Well, this is a trivial statement about inner product. So, if I take an alpha in the complex plane and f and g in your space L2 of mu. So, remember L2 of mu is a vector space with an inner product. T of alpha f plus g equal to, well, g is already used. So, let's take h here instead of g. Okay, so I'm taking two functions in L2. Okay, so this is by definition inner product of alpha f plus h times g of g. Well, this you can write as an integral if you want. So this is alpha f plus h times g bar d mu, right, which is of course by linearity of the integral etc. this becomes alpha of Tf, which is f inner product with the g, plus Th, where this is h inner product with the g, right, which means T is linear. Okay, so that is why T is linear. Well, it's not just an arbitrary linear map, it has certain continuity property. So recall that L2 has a is a metric space, right. Whenever you have a norm, there is a metric on the space, right. What is the distance between two functions? Distance between f and g is nothing but the norm of f minus g, right, the L2 norm. It's a metric space and it's complete with respect to this metric space. So we proved that LP is complete with respect to the LP norm, right. LP norm gives a matrix and with respect to that metric it is complete. Okay. So since it's a metric space, we can talk about continuity. Okay, so it's so the map T is actually continuous. What does that mean? That is, if Fn converges to f in L2, right, so that is same as saying dFn f, which is equal to the L2 norm of Fn minus f goes to 0, right. Then continuity means if Fn converges to f in the space, then the image convergence should happen, that is Tfn, but Tfn's are complex numbers, right, converges to T of f. So this happens in the complex plane. Well, why is this true? So that is because it's given by an inner product, and that's the reason. So let us look at Tfn minus Tf, right. This is what we want to actually compute and see whether it goes to 0. So Tfn minus Tf, because T is linear, I can write it as T of Fn minus f, but T is simply taking the inner product of Fn minus f with something, right. So this is Fn minus f inner product with g. Okay, I want to say this goes to 0 because Fn converges to f, right. So I am starting with the sequence Fn converging to f in L2. So let's look at the modulus of this. Okay, so this is equal to this. So here I can use Cauchy-Schwarz inequality to get Fn minus f L2 norm of g, right, and this of course goes to 0 as n goes to infinity, right, because Fn goes to f. So in the left hand side we will get, so this tells me that T of Fn converges to T of f, which is precisely what we want, right. That is what we meant by a continuous function. So the upshot of all this is that the linear map which we define T, this is a continuous linear map. Okay, so taking the inner product gives me a continuous linear map. The converse is also true. So that is the aim of these two lectures today. So aim, any continuous linear map, okay, it's called a functional. So from L2 of mu into C is given by an inner product. Okay, so this is what we want to prove. So we just saw that if I take the inner product with the fixed function, it is a continuous linear map. Okay, so our aim is to prove the converse. So this is called the Riesz representation theorem. Okay, so this requires some preparation. So, and you will see that most of the time we use only the inner properties of the inner product. Okay, so nothing very particular about L2, but we will use the fact that it is an inner product space every now and then. Okay, so let us start with some simple definitions which you already know. Convex sets. Okay, So let's say V is a vector space over R or the complex plane. Okay, take a subset in V. Okay, we say E is convex. E is convex if for every x and y in E, the point Tx plus 1 minus Ty. Okay, so this happens for all t between 0 and 1 also belongs to E. So this you can think of as the line joining x and y, right? When t is 0 you get y, when t is 1 you get x. So if I have, so let's draw some pictures to see that what is convexity in the simpler cases. So if I have a set like this is of course convex, right? Because if I take 2 points, any 2 points, the line joining them is entirely inside. But if I have some dent like this will not be a convex set, because if I take a point here and point here, the line joining them goes outside, right? So this part is outside the set, so it will not be convex. Okay, so this is convex, but not, this one is not convex. Okay, so convexity simply means that you take any 2 points, the line joining them should be inside that set. Okay, so convex sets are somewhat important. You will see, well, one of the reasons now. So let me write it in this form. Let me write it as a theorem. Okay, every non-empty closed, so all these assumptions are important, closed convex set. So you take a non-empty closed convex set E contained in L2 of mu. So everything makes sense, right? Non-empty closed, because L2 mu is a metric space, so you know what is meant by closed. Convex we just defined. So you take a closed convex set E in L2 mu, then E contains a unique element of smallest norm. Okay, what does that mean? That is, there exists a unique, so the exclamation mark here simply means unique. There exists a unique x naught in E, well, x naught, so let us use the functions because we are in L2, right? So I have some function f naught in L2 of mu in E, which is the unique element with smallest norm. So that means the L2 norm of f naught, right, that is the norm, that is actually equal to the smallest one. So that is infimum of L2 norm of all functions g, where g is in E. Okay. So every non-empty, so all these are important, non-empty closed convex set, okay, that is the part. So any such one will have a element with minimal norm. That is the assertion of the theorem. Okay, so let's see the proof. Okay, so first thing is check the identity. So this is a trivial computation which you can do. All you have to do is to expand appropriate integrals, check the identity. So this is for f and g in L2 of mu. Okay, integral over x mod f plus g square d mu plus integral over x mod f minus g square d mu equal to 2 times integral over x mod f square d mu plus integral over y mod g square d mu. Okay. So, this is called the parallelogram law. Parallelogram law. Well, I will not say much about this. So, all this requires is an inner product. Okay. The norm should come from an inner product and this will be true. Well, how will you prove this? So, so all that you have to do is to expand. So, mod f plus g square is f plus g. So, these are complex valued functions, right. So, you take the complex conjugate and then multiply, right. So, when you multiply it, you will get mod f square, mod g square, f g bar, f g f bar, etc. and certain things will cancel and whatever remains will be whatever is on the right hand side. So, it is a straightforward computation. Okay. So, I will leave it to you. So, remember the parallelogram law, we will need that. Okay. Now, so we have a set E which is contained in L2 of mu. It is closed, non-empty, closed, convex, right. We know this much about it. We are trying to find out a minimal element there. So, element with minimal norm. Okay. So, let delta equal to infimum of all the norms, right. So, mod f square d mu to the half, right. So, this is the norm. So, L2 norm of f, right, where f is in E. So, you look at all those guys in E, look at the infimum and then find out, let us call that delta. Okay. Now, if I take any two elements in E, suppose f and g are in E, then f plus g divided by 2 is also in E, right, by convexity, right. 1 by 2 plus 1 by 2 is 1. So, any convex combination will be in E. Okay. Now, apply parallelogram law. Apply parallelogram law. Well, what do we get? We get, so I am applying parallelogram law to f by 2 and g by 2. Okay. So, to f by 2 and g by 2. Okay. So, let us go back to the statement here. So, this is the parallelogram law, right. So, I will have, if I write f by 2 g by 2, I will have a 1 by 4 coming out, similarly 1 by 4 coming out here. 1 by 4 comes out and it will cancel with 2 and similarly here. So, this will become half, right. So, if I write only this part, the first term I will take to the other side. Okay. So, apply it to f by 2 and g by 2, you will get 1 by 4 integral over x mod f minus g square d mu. Okay. So, that is this part, okay, equal to, then I write both of these two terms, but remember there is a 1 by 2 here. So, 1 by 2 square 1 by 4 and 2 gets cancelled. So, you will have a half. Okay. So, half integral over x mod f square d mu, there is no problem, plus half mod f square, sorry, mod g square d mu over x. So, that takes care of these two terms. Now, there is one extra term here which I take it to the right hand side to get minus. Okay. But remember f and g replaced by f by 2 and g by 2. So, I have a 1 by 4 integral over x. Well, instead of 1 by 4, I'll just take the 2 inside because I want to use the fact that E is convex, right. So, I have f plus g by 2 square dv. Okay. So, recall that f plus g by 2 is in E because E is convex. Okay. So, if E is if f plus g by 2 is in E, then look at this quantity delta. Delta is the infimum of such things, right. So, this quantity is greater than delta. So, if I replace this with delta, I will get a bigger term on the right hand side because I am subtracting, right. So, let me write this as this gives me this is less than or equal to half mod f square. Okay, so I can take the 1 by 4 to the other side. So I will get integral over x mod f minus g whole square d mu. So 4 when I take it to the other side, I'll have 2 integral over x mod f square d mu plus 2 integral over x mod g square d mu. Okay, I should be writing minus delta square, but then 4 comes to this side, to the right hand side, so I'll get minus 4 delta square. Okay, remember delta is much smaller than whatever is here, and so I'm subtracting a smaller quantity, so that is why I have the inequality less than or equal to. Okay, so now we are in a position to prove the theorem. So let's go back to the statement of the theorem. Every non-empty closed convex set E contains a unique element of smallest norm. Okay, so first we will look at the uniqueness part, and then we will prove the existence. Right, there are two things. So uniqueness. Okay, so uniqueness. Suppose F1 and F2 are in E and they attain the minimum. So that means L2 norm of F1 and L2 norm of F2 are same as delta. Remember, delta is the infimum of such things, right? We want to show that there is one element which attains the norm delta and there is only one element. Suppose there are two elements. Then you plug it in here. Well, what do I get? Integral over x mod f1 minus f2 whole square d mu, right, is less than equal to 2 times the norms of these two, right, f1 and f2 is delta. So that is 2 delta square plus 2 delta square, and I have minus 4 delta square, which is 0. Okay, so this is a positive quantity less than or equal to 0. So this implies f1 equal to f2 almost everywhere. So remember, when they are almost everywhere, we identify them, right? So that is why there is uniqueness. There is only one function which can do this. But of course, it does not prove that it exists, right? If there is a function, there is only one function. So existence. So next thing is to prove that there is some such function, existence. Okay. So let's go back to the definition of delta again. So delta is infimum of L2 norms of f, where f belongs to E, right? The closed non-empty convex set. So remember, the convexity we have already used, right? Because the midpoints are in. So here we use that E is convex. Now we will use that E is closed as well. Okay. So because delta is the infimum, I can choose a sequence. So choose a sequence Fn in E such that the norms converge to L2 norms of Fn's converge to delta. Okay, so that I can do. So let us say the earlier inequality. So I should use some term for this. So let's say 1. Okay. So use 1. See, 1 is true for any two functions from E, right? So I can use it for Fn. Okay. We get integral over x. So I use Fn minus Fm square d mu, right? So Fn g, this is less than or equal to 2 times integral over x mod Fn square d mu plus 2 times integral over x mod Fm square d mu minus 4 delta square, right? So this is from this inequality 1 because the functions are in E. Okay. Now, well, what happens to the right hand side? So this, as n goes to infinity, L2 norm of Fn's go to delta. So this goes to delta square, this goes to delta square. So I'll have 2 plus 2 plus 4 delta square, and there is a minus 4 delta square. So the right hand side goes to 0. So what I am saying is this goes to 0 as n and m go to infinity, which is same as saying Fn is Cauchy, right. Hence Fn, this is contained in L2 of mu, right, is Cauchy, is a Cauchy sequence, but L2 is complete, but L2 mu is complete with respect to that norm, right, is complete. So there exists some f in L2 mu such that the Cauchy sequence will converge to f, right. So such that Fn converges to f. Of course, the convergence is happening in the same metric space, but Fn's are in E, right, but Fn's belong to E, and E is closed. E is closed. So its limit points will be, E's limit points will be in E, and f is a limit point, right. So this implies f is in E. Of course, Fn's converge to f in L2 of mu. So this immediately implies the L2 norm of Fn's will converge to L2 norm of f, right, but this is actually converging to delta. So these two will have to be equal to delta, right. So f L2 norm is delta. So what we have done is we have constructed an f in E whose norm is delta, which is the minimum of the elements in E. So any closed convex set in L2. So let us go back to the statement of the theorem. Any non-empty closed convex set E in L2 contains a unique element of smallest norm. Okay. All right. So we finish here. So let us stop here. We have just started with some properties of some elementary properties of the L2 space. Okay, L2 space has the extra structure of the inner product space, and so there are various things you can do easily because of the inner product space. So all that we have proved right now is that any closed convex non-empty subset of L2 of mu has an element of minimal norm, smallest norm. Okay. So if you look at the proof, you will see that the facts we used about L2 was that it is an inner product space. The inner product gives a norm, and with respect to the norm, the space is complete. Okay. So such spaces are called Hilbert spaces. So L2 is an example, and when you learn more of functional analysis, you will see that any Hilbert space can be realized as L2 of mu for some measure mu. Okay. So you can think of this as a general result if you want, or stick to L2 of mu if you like. Okay. So we will continue with this. In the next session, we will prove that all continuous linear functionals are given by inner product. Okay.